to my computer. Trying to get these recordings out as quickly as I can, as hopefully many of you are noticing. So it takes a couple of hours for them to be put in the form that's needed on the site. So I cannot, unfortunately, cannot put them out there immediately. What I can do is, obviously, I can immediately get those notes that I have to you. But in terms of getting those videos up there, for those of you who are utilizing the videos, and I know some of you are looking at them, but to get that video information up there, I unfortunately cannot do that immediately. It takes a little bit of time. Okay, let's pick up with any questions that we have from where we left off on yesterday before we get going. Any questions on any of the material that we had from yesterday? Questions or comments? I know a lot of the comments are going to be, this is way too easy, please give us something harder. So let's hold those comments off for a while. No comments, no questions. Okay, well, let's pick up with impedance, where we were at yesterday, to make sure that we're all on the same page. So we talked about impedance. We said Z was the letter that we used for impedance. And the definition of impedance, Z was defined to be equal to some V phasor divided by some I phasor. In general, what we're thinking of is the following. I have an impedance here. I'll call that Z. And Z is going to be defined, or we can relate it the following way. If there's an I phasor that goes into the positive terminal of the voltage V phasor, whatever that Z is, then we know the relationship is V phasor is equal to I phasor times Z. All three of those quantities in general are complex numbers, but we said something about V and I phasor with regard to them being a phasor, and Z with regard to it being a complex number but not being a phasor. And we established that Z is not a phasor, it's just a complex number, it doesn't get a bar over the top of it. And the reason that Z is not a phasor is because Z is not representative of a time-varying sinusoid. So we've got this relationship between the voltage and the current in the frequency domain that is very similar to the relationship we have between the current and the voltage in the time domain for a resistor. The beauty here is this voltage-current relationship is for all impedances. And we know that every element has its impedance. And we can combine things together to have complex impedances. So we know individually for a resistor, we know that the impedance for a resistor, Z sub R, is nothing more than the resistance itself. We love that, that's easy. For an inductor, we know when we transform the inductor into the frequency domain, that the impedance for an inductor is going to be J omega L, purely imaginary, purely real, purely imaginary, and for a capacitor, that impedance can be written a couple of ways, but the way that I like to write it is that it's minus J divided by omega C. And we looked at what that means in terms of a lot of things. So one of the things it means that we didn't talk about in detail yesterday is, remember, all of this that we're doing, you have to always in the back of your mind remember the following, because it is easy to forget. All of this is only for sinusoidal inputs for circuits. Only. If you put in another input that is different than a sinusoid, if you put in a DC input, an exponential input, a square wave input, all of the other inputs, no matter what you put in, we cannot use this method. This method is only useful for sinusoidal inputs. So since it's for sinusoidal inputs, we can make some recognitions about the current and the voltage in terms of their phase differences. So let's take a look at that for the resistor. And we talked about this when we actually drew a picture yesterday. V phasor is equal to I phasor times R. So R is just a real number. So if we let, in all of this, let V phasor equal V sub M at an angle of theta V. Let's let I phasor equal I sub M at an angle of theta I. This is what we know. So this is going to be V sub M at an angle of theta V equals I sub m at an angle of theta I times r, which is nothing more than r times I sub m at an angle of theta I. So when we look at this and we compare both sides, this is something you need to get used to. When we compare, we have this equality. This equals this. There's only one way that two phasors can be equal to each other. There's only one way that two phasors can be equal to each other. They must have the same amplitude. So one, this implies V sub m must be equal to r times I sub m. And the phases must be equal. They have to have the same phases. 2, theta v equals theta I. And this is what I want to focus on right now in the short term. This means theta v and theta I are the same exact phase angle. That means the current and the voltage are in phase. This is for a resistor, are in phase. And we looked at that yesterday and we drew a picture of what it means for them to be in phase. They have the same phase shift, so they are aligned. Zero crossings for the current and the voltage aligned. The only difference between the two is that they have a different amplitude. So when we go to the time domain, we know the frequency is the same for both of them. So they have the same frequency. I'm not going to try to draw pretty pictures today. They have the same frequency. So one of them looks like that. The other has the same exact frequency, but it has a different amplitude. So it might look like that. So they are in phase with each other. Now let's go to, that was the resistor. Let's go to the inductor. So we know for the inductor, we know that Z for an inductor is equal to j omega L. So this is what we have. So we have V phasor is equal to I phasor times Z. In this case, it'll be Z sub L. Okay, let's do the same thing. V phasor is V sub m at an angle of theta V. I phasor is I sub m at an angle of theta I. And Z sub L is j omega L. Now to make this comparison, I want to make the comparison in the frequency domain, and I want that to be in polar form because it's really easy to do it in polar form. By the way, if we do it in rectangular form, for two complex numbers to be equal, the real parts must be equal and the imaginary parts must be equal. In polar form, they must have the same magnitude and they must have the same phase. So there's always two things that have to be equal to each other. Okay, I'm going to be clever here. I hope you think I'm clever today. This is I sub m at an angle of theta I times j omega L at an angle of 90 degrees, right? This is purely imaginary, purely imaginary. Okay, this is omega L I sub m, so that's how it affects the amplitude, omega L I sub m, at an angle of, remind me what I do to the angles when I multiply?
Add.
Excellent. Theta I plus 90 degrees. So let's compare now what we have. So this V sub m is going to be omega L I sub m. We're not focusing on the amplitude, but we're focusing on the phase angle. So theta V is equal to theta I plus 90 degrees. So this tells us that the phase angle of the voltage is the phase angle of the current plus 90 degrees. I'm going to write that in words for you. The phase angle of the voltage, I'm going to write it one different way than the way I said it, is 90 degrees more than the phase angle of the current. So for the inductor, if I have, I'm just making it up, if I have an inductor current. Okay, so let's this one be the current. And I'll make the voltage smaller in amplitude so you can see it. What does it say about the voltage? The voltage is the same phase angle as the current right there. It's the same phase angle plus 90 degrees. It's 90 degrees more. Plus 90 makes it shift in this direction. Negative makes it shift in that direction. Negative, positive. So it's going to be shifted over by 90 degrees. This from here to here is 90 degrees. It's 90 degrees. Don't worry about what it is in time. It's 90 degrees. So the voltage is going to be shifted by 90 degrees. It's going to look something like this. Okay? So the voltage leads the current by 90 degrees. In an inductor. Actually, it's the voltage, I want to say for an inductor, not in, because there are no voltages in inductors. There are voltages across inductors. The voltage for an inductor leads the current by 90 degrees. The one thing I used to use a lot of sleep over is I used to think, well, how the heck can the voltage happen first and then the current is delayed? It's not that one happens first and the other is delayed. It's not that. It's just the both of them are happening at the same time. They're continuous functions. It's just the phase difference between the two is 90 degrees. So we say the voltage leads the current by 90 degrees. We're always going to see this 90 degrees when we're talking about pure elements, resistors, capacitors, and inductors. Here, if we went back to the resistor, they're in phase, neither leads the other. They are both aligned perfectly. So neither of them are leading or lagging. Okay, another way to say this is the current lags the voltage. Lags the voltage. So we use leading and lagging. They're important terms for us. And it lags by 90 degrees. So that's for an inductor. I'm going to show you something that will help you remember this. I think I gave it to you before, mentioned to it, but now you'll see where it plays a role. Okay, so let's continue and let's look at the capacitor. So the capacitor, we know, again, Z sub C for a capacitor is equal to minus J over omega C. And now, V equals I times Z sub C. So what we're going to have is, we're going to write this, V sub M at an angle of theta V is equal to I sub M at an angle of theta I times Z sub C, times Z sub C, minus J over omega C. If I put Z sub C into its polar form, and I will do that right here, I sub M at an angle of theta I times 1 over omega C at an angle of minus 90 degrees. Purely imaginary, but negative. Purely imaginary and negative. I'm going to do the same thing here and write this the following way. It's I sub M over omega C, and that is going to be at an angle of theta I minus 90 degrees. So what does that tell us? That tells us the relationship is the following. The amplitude of the voltage is equal to the amplitude of the current divided by omega C. And 2, the angle, theta V, what I'm really interested in today, is the angle of the current minus 90 degrees. Notice it was very similar to the other one, except rather than a plus, it's a minus. So in words, what does that tell us? This tells us for a capacitor, the voltage lags the current by 90 degrees. Or another way of saying it is the current leads the voltage. Depends upon which one you're talking to. And there's no preferred reference. There's no preferred reference. Like the reference is always the voltage. So always give it with respect to the voltage. Okay. So what do those pictures look like? Well, in this one here, if this was the current and this was the voltage for the inductor, it's just the opposite. For the capacitor, this one is the current and this one is the voltage. They just switch. Here's something to help you remember all of this. I hope it helps you remember it. Or you might remember me talking to you about Eli the Iceman. So Eli the Iceman really is about helping you understand what comes where in terms of the current and the voltage, which one leads, which one lags. So here for Eli, remember E equals V. E is electromotive force. And we use V. So way back at the beginning of the semester when we started, we talked about electromotive forces, and you will still find textbooks that use E for voltages and not V's. So for L, the inductor, E comes before I. Voltage in an inductor leads current. Voltage leads the current. For the capacitor, current for the capacitor leads the voltage. Current for the capacitor, voltage. So this little gimmick might be helpful for you in case you need to remember or recall what leads what, which one's leading, which one's lagging, okay? Now, in general, in impedance, in general, and we're going to spell out a lot about impedances today, is somewhere between, it's going to have or will have, a phase angle that's not zero, that's not plus 90, it's not minus 90, that satisfies the following. Because our elements in resistance is never negative, because resistance is never negative, we know the following. So we'll call it theta z, phase angle, theta z. Theta z is always going to be in the following range. It's going to be between minus 90 degrees, and it's going to be between plus 90 degrees. The phase angle is always between minus 90 and 90. Three very specific cases are when the impedance is purely real, purely resistive, is 0 degrees. When it's purely inductive, it's 90 degrees. And when it's purely capacitive, it's minus 90 degrees. But in general, it satisfies that range right there, somewhere between plus and minus 90 degrees. Okay? That range right there. Okay, we're going to see that today as we expand on what we had. So let's pick up where we ended yesterday. We talked about series impedances. And so we said everything that we had about resistors, we have about impedances. So series impedances, we know that they add. So Z equivalent, if I have a bunch of them in series, it's going to be Z1 plus Z2 plus Z3 plus ... plus Z sub n. So they add when they're in series. And I showed you an example of that with a picture. Let's look at what happens when they're in parallel. So parallel impedances. So parallel, picture of that. Z1 Z2, Z3. I think we had a picture of this yesterday as well. Z sub n. When we look in here and we say, well, what is the equivalent single impedance that will have the same terminal effects at A and B? What single impedance? The answer is 1 over ZEQ is equal to 1 over Z1 plus 1 over Z2 plus 1 over Z3 plus dot, 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 1 over Z sub n. Usually we don't like that. We like what, not what's 1 over Z equivalent, what's Z equivalent. So Z equivalent is equal to 1 divided by 1 over Z1 plus 1 over Z2 plus 1 over Z3. But all semester long, I don't think one of you, and I could be wrong, I don't think one of you has used this equation. Because what did we say to do when you have multiple things that are in parallel? When you have multiple things in parallel, what do we say to do?
Just to product over sums and then keep moving along.
Yeah, just reduce it to 2, product over the sums, then you'll have that one, and then group it with another one, and just continue grouping with 2's. So for two parallel impedances, we know Z equivalent is equal to the product over the sums. Everything is the same. There's one thing that's different. I wish I could change it for you. These are complex numbers. All right, let's look at an example. So let's find the equivalent impedance for the following. Impedance. Seen to the right of terminals AB. So here's the circuit, or the portion of the circuit. Here's A, here's B, and to the right of it, I have a 3 ohm resistor. I have an inductor whose impedance is J2. We'll ask a question about that in a moment. I have a capacitor here, and that capacitor is, let's make that negative J3. Notice it's got to be negative. If I put in positive, there's clearly something wrong, clearly. And 1. By the way, we didn't accentuate this or talk about it, but all impedances are measured in ohms, all of them. So if I were labeling this, this would be ohms, this is ohms, this is ohms, this is ohm. Everything's in ohms. I know resistors were in ohms. Impedance is also in ohms because it's a voltage divided by a current, and the unit of voltage divided by current is ohms. Okay, so I think all of you can see that those two are in parallel. So let's solve for what that is. Let's call this Z1. Z1 equals minus J3 in parallel with 1. And that's equal to the product over the sums. Minus J3 times 1 over 1 minus J3. That equals minus J3 in the numerator divided by 1 minus J3 in the denominator. And I would tell you that because I'm looking forward and I know that I'm going to add this to 3 plus J2 because it'll all be in series, what form do I want this impedance Z1 in right now?
Rectangular.
Absolutely, it's got to be rectangular. Yeah, I'm going to add it later on. So I have to be in rectangular form. So for that reason, what I'm going to do is I'm going to multiply by 1 plus J3 over 1 plus J3. Let's get rid of this denominator in the complex form to make sure that all we have is a constant. So when we do that in the denominator, we get 1 squared plus 3 squared. 1 squared plus 3 squared. We'll figure out what that is. And in the numerator, I have minus J3, and then I have a minus J3 times a J3. The J squared is -1. The negative times that -1 is a positive, and that's going to give me a positive 9. So this is going to be equal to 9 minus 3J divided by 10. Don't forget, this is equal to 9/10. I don't want you to necessarily write it this way, minus J 3/10. I just want to be sure that you see this is real part plus imaginary part. Okay, awesome. Well, ZEQ is equal to 3 plus J2 plus Z1, which is 3 plus J2 plus, let's just use the last form that we have here, 9/10 minus J 3/10. That look like a plus. And now I just add the real parts. So 3, oopsies, where'd you go? Right there. 3 plus 9/10. 3 is 30/10 plus 9/10. That's equal to 39/10. That's the real part. The imaginary part, 2 is 20/10 plus J. 20/10 minus 3/10 is 17/10. So you can leave it that way, or you can write it this way. Equals 39 plus J 17 divided by 10. Your preference. And that's how we play the same game with impedances. Now look at what we just did. You've got to convince yourself. That was pretty awesome. We just took a component of a circuit. It had a capacitor, it had an inductor, it had resistors, and we added all of that together. Whoa, how about that? I didn't know I could do that. Just slide that. Waited. Oh, I guess maybe it blew it up for me or something. I don't know. Just leave it alone. I won't worry about it. So we added it all together and got one single impedance right there. One element. And what we would do is we would do the following. A, B. You want to replace this by a single element. We draw it like a box. And we just write the following. 39 plus J17 over 10. I know I wrote that real small. But if we wanted to, we could, I want you to think back in this form here, and I could do the following. See if you agree with this. Same thing. So I like the first approach, but we could also do this. And I could write this as 39/10 and this as J 17/10. They're in series, they add. That's what that says right there. They add. How did I know it was an inductor and not a capacitor?
Because the J was positive.
Outstanding, Jack, because the J was positive. So when we look here at this Z, somebody's going to say, oh, you've got a load. What kind of a load is it? And you're going to say, it's an inductive load. They're going to want to know, is it inductive or is it capacitive in nature? And we look at the imaginary part and we see, is the imaginary part positive or is it negative? When it's positive, it's an inductive load. And when it's negative, it is a capacitive load. So we're going to talk a little more about impedance, but at the same time, I want to talk about admittance. Okay? So more on impedance, more on admittance. So let's go back to this relationship. V equals I phasor times Z. And let's now let the following be true. Let's let V equal Vm at an angle of theta V. Let's let I phasor equal Im at an angle of theta I. And then finally, let's let Z equal magnitude of Z at an angle of theta Z. Now, everything that we're going to do is going to be obvious, but I want to spell it out clearly. Here's my Z. Here's my I phasor. Here's my V phasor. Notice everything that we had from week 1, week 2, when we talked about the passive sign convention, still stays. We are so ingrained with the passive sign convention, we haven't even used that terminology in a long time. Same thing, I enters the positive terminal of the voltage V. Okay, so we know that Z, which is equal to magnitude of Z at an angle of theta Z, is equal to V phasor over I phasor. We know that by definition, but that's V sub m at an angle of theta V divided by I sub m at an angle of theta I. Oh my goodness. Take this, take this. For those two to be equal, what two things must be true? One, maybe I need to do a little bit more math on this. Equals V sub m, and let's push this over just a little bit, equals V sub m over I sub m at an angle of theta V minus theta I. All right, number one, what must be true? I'll start you. Magnitude of Z is equal to
VM over IM.
Thank you, very nice. So the magnitudes of these, the amplitude, the magnitude of these voltages, all you have to do is look at the magnitude of the voltage and the magnitude of the current. The magnitudes, the ratio of those gives you the magnitude of the impedance. Second relationship, what about the angle of the impedance? It's equal to?
Is it theta V minus theta I?
It is correct, Jordan. Outstanding. Theta V minus theta I. So these things don't just happen on their own. The impedance, really what's going to happen is the current. You can look at this in a number of ways. And here's one way that I look at it. I look at it like the following. Oh, I know what's going on. Theta I is governed by theta V minus the angle of the impedance. So once I know the angle of the voltage, I just subtract the angle of the impedance, and that will give me the angle of the current. That's the way I see it. It's interesting that other people see it different, and they see it this way. Well, I'll tell you what the angle of the impedance is. The angle of the impedance is the angle of the voltage minus the angle of the current. I don't care which way you see it. They're both great equations. They both work, and they both tell us what's going on in the world of impedances. So these are two very nice equations that can be used to help understand what's going on. Now, more about the impedance. So we're writing Z is equal to magnitude of Z at an angle of theta Z. But we can always write this in rectangular form. So when we do, this is the way we write an impedance in rectangular form. R, you can probably imagine why we use R, but you probably don't know why we use X. Don't worry about it. R plus JX. So R is obviously equal to the real part, and we know that the real part of an impedance is the resistance. It's where the resistors play a role. So it's the real part of Z, and we call that the resistance. So all along we've had that. And x, which is equal to the imaginary part of z, is called the reactance. So there's resistance and there's reactance. Now, you and I both know that we can always easily go from polar form to rectangular form, and vice versa, from rectangular form to polar form. So let's do that and show if I had this form, if I have the polar form, how do I find the rectangular form? So R is equal to, see if you agree with the following, the magnitude of z times the cosine of theta z. And x is equal to the magnitude of z times the sine of theta z. We're just converting rectangular to polar. I'm sorry, polar to rectangular. Or going the other way around, the magnitude of z, if I have r plus jx, which we had in the last example, r plus jx, the magnitude of z is nothing more than the square root of r squared plus x squared. And we have that part, that's the magnitude of z. The other part is theta z. How do I find theta z? Theta z is equal to the tan inverse of the imaginary over the real, x over r. I know the previous example was an ugly one, but let's continue. Example continued. So what did we have on that last one? On that example, we had 39 tenths plus j 17 tenths, or 39 plus j 17 divided by 10. So ZEQ was equal to 39 plus j 17 divided by 10, which is equal to 1/10 times 39 plus j 17. Let's take this part here and let's convert that. So this is equal to 1/10 times, converting it, the square root of 39 squared plus 17 squared at an angle tan inverse of 17 over 39. I'm just going to give you some numbers so you have some numbers. So let me just pull out my handy calculator. So it's this times, so I have a calculator on, let's clear that. Squared plus 17 squared. And I'll take the square root of that. So square root of that is equal to 42.54. 42.54. Generally, I use 1 or 2 decimal places. That is typically plenty. And the angle is, I have the tan inverse of 17 over 39. So let's see what 17 over 39 is. Let's see what my tan inverse of 17 divided by 39. And that is 23.55 degrees. We knew it was in the first quadrant. Positive J, it was in the first quadrant. So overall, I'm just going to take that 1/10 and pull it inside. ZEQ is equal to 4.25. I'm going to leave it like that. And an angle, I'm just going to throw away one of those decimal places of 23.55 degrees. So we can convert from one form to the other. We should be very comfortable going in both forms because you know that when we're dealing with complex numbers, there are times when we want those complex numbers to be in polar form, and there are times that we want them to be in rectangular form. So we can look at x. We can look at x. If x is negative, we know that when x is negative, our reactance is a negative number. We have a capacitive load. When x is positive, our reactance is positive, and we have an inductive load. So we can figure out a lot just by looking at that piece of information. Okay. When we had resistors, just recall, we had a quantity G, and that was defined to be equal to 1 over R. Here, we have our admittance, which is not G, which is Y. And Y is defined to be 1 over Z. By definition, Y is 1 over Z. And we have admittances for the same reason we have G's, conductances. The reason we have that is because when things are in parallel, sometimes it's way easier to deal with 1 over Z than it is to deal with the Z part. So admittances in general are used when you have parallel type components going on. So we can look at this in a variety of different ways. So let's look at it. Let's start this one way. Here's the easiest way. Y is equal to 1 over Z, which is equal to 1 over magnitude of Z at an angle of theta Z. That's the easiest way to do division. This is equal to 1 over the magnitude of Z at an angle of negative theta Z. Numerator angle is 0 minus denominator angle. So therefore, what does this tell me? This tells me if Y is equal to the magnitude of Y at an angle of theta Y, then we know, comparing this one to this one, we know the following. The magnitude of Y in terms of Z is equal to 1 over the magnitude of Z. We know that the angle of theta Y, which we'll call the angle of Y, which is theta Y is equal to minus theta Z. So they have the same angle but opposite in sign. So interesting. When the impedance is in quadrant 1, the admittance is in quadrant 4. Okay, so that's one way to look at it. There are many ways to look at this. Let's do this the other way. So Y is also defined to be equal to G plus JB. You can probably imagine why the G was used. We had the same G as before. It is the same G. And so we know that this is equal to 1 over Z, but that's equal to 1 over R plus JX. So I'm going to do this all in rectangular. Let's multiply that by R minus JX over R minus JX. So I'm multiplying by the number 1, and I'm going to get the following. This is R minus JX, all divided by R squared plus X squared. If I look at this, I can clearly see the real and the imaginary part. I'm going to make sure I spell this out properly. So G plus JB is equal to R divided by R squared plus X squared minus JX over R squared plus X squared. That tells me G is equal to R over R squared plus X squared. And then it tells me that B is equal to minus X over R squared plus X squared. Don't drop the negative sign. So we're highly in mathematical mode right now. So we can see that look at this one here. What happens when I have a purely resistive impedance? What's the value of X when I have a purely resistive impedance? What's the value of X?
0.
Good. And so what does G become when X is 0?
1 over R.
Correct. Same G that we had before. Surprise, surprise. Should be no surprise. We make sure that everything works with the world that we had. By the way, what is B when it's purely real? When the impedance is purely real. We said X was 0. What is B?
0.
Excellent. B is 0. So when we have a purely real resistance, it tells us that our admittance is purely real. We just have a G part and not a B part. So we can see that all of those things are related to each other. There's a great relationship. It's wonderful. We love that relationship. They're really nice. Okay, let's do the following. Let's pause right now. Let's take our break a little earlier today. And now I'm going to work forward on phasors and the circuit analysis with phasors. So right now, let's take ourselves about a 5-minute break. We'll come back after our 5 minutes, and then we're going to get into the world of utilizing all of this information we've had, but more importantly, utilizing the phasors and the impedances that we have to do circuit analysis and write down all of the things that still pertain that we had and what things don't and why don't they. So we'll get into that when we come back. So I'm going to put us on pause here and on our recording. We'll come back in about 5 minutes. Beautiful. Comments, questions? G plus JB, R plus JX, impedance, admittance, phasors. Any questions on any of that? All good stuff, all great stuff. You're loving it. You know what's interesting? We've been spending a lot of time on phasors now. We've been spending a lot of time in the frequency domain. We're working with impedances and stuff like that. And so far, we really still haven't seen how it makes our life easy. So we haven't really done any circuit analysis to solve for any currents or any voltages with regard to these phasors and how they work. And by the way, that reminds me, I did something yesterday. I mistakenly did something. Shame on me for doing that. Let me just point that out. I talked about a multiplication in the time domain, like multiplying a cosine times another cosine. I don't know if you remember that. And I told you how you can do that in the frequency domain, and that was my mistake. You can do it when you add or subtract them. You can't do it when you multiply them. That's where this breaks down. It's where it breaks down, and it has to do with the real part and the imaginary part and whether or not they follow properties of linearity or not. And you don't know about that, you don't care about that, but what I showed you was incorrect yesterday, so you just erase that from your notes. It's not true. It doesn't work for multiplication. It works for addition and subtraction. For example, this you can do. You can say 3 cosine of 2t plus 45 degrees plus 3. Let's put a 3 out front there. 3 plus 5 cosine of 2t plus 30 degrees equals what? And we can solve this in the frequency domain by going to the phasor form. 3 at an angle of 45 degrees plus 5 at an angle of 30 degrees equals. Then just stop breaking it up. We're adding, so we know we have to put this in the rectangular form. So this would be 3 root 2 plus j 3 root 2 plus 5 at an angle of 30 degrees. Cosine is root 3 over 2, so it's going to be 5 root 3 over 2. Sine is going to be 1/2 plus 5 halves. I know these are ugly numbers. I don't want you to worry about the ugly numbers. Then you would add them. 3 root 2 plus 5 root 3 over 2. Let's just pretend that that value is, I don't know, little a plus j. And then I have 3 root 2 plus 5 halves. And just pretend that that value is b. So we have, this is a plus jb, knowing what a is, knowing what b is. And now this is equal to the square root of a squared plus b squared I don't know why that disappears. It happens from time to time. A squared plus b squared at an angle tan inverse of b over a. And now we're going to convert back to the time domain. Cosine, what goes out in front? Square root a squared plus b squared, 2t plus tan inverse of b over a. I showed you a multiplication yesterday. I got way out over my skis on that one. So that's how you can add and subtract sinusoidal functions that are of the same frequency. They must be of the same frequency. So you can do that. Okay, let's pick up and continue forward. Let me just mute the video here, come back up over here and continue. Okay, so if there are no questions, what I want to do is I want to look at circuits and the laws of circuits with regard to phasors. Phasors and circuit analysis. Okay, so nearly every law that we've been using, every rule that we have been using in circuit analysis still holds true. So the following concepts, laws are still valid with phasors and impedances. All right, here we go. So list of a good number of them. So let's start with number 1, KVL. That still holds, still true. Number 2, KCL, still true. So just examples of these. For example, I1 phasor plus I2 phasor plus I3 phasor equals 0. That's an example. Actually, vice versa, switch these around. That one there, right? V1 phasor plus V2 phasor equals 0. Those would be examples. KVL and KCL, they still work, they still hold. Ohm's law, still. V equals I times Z. That's the only change. It's not R, it's I times Z. Current dividers. We like using current dividers when there are 2 of them, right? So for 2, it would be I1 phasor equals, and then it's going to be the impedances like Z2 over Z1 plus Z2 times I, I'll just call it times I, for example. These are just examples. Voltage dividers. So that would be V1 equals Z1 plus Z1 divided by Z1 plus Z2 all times V. So that's all valid. Current and voltage dividers, awesome. KVL, KCL, Ohm's law, current dividers, voltage dividers. We've just seen series and parallel impedances. So we spent our time with that earlier today and in our last lecture yesterday. Couple more, or a few more. Nodal analysis. Oh, you're kidding me. I can still use that. I was hoping we could throw that away. Mesh analysis. So those concepts still work. Source transformation, no way. Some textbooks go through and prove that all of these are still valid. I'm just telling you, you're not going to be really interested in the proofs. So source transformation works. Series and parallel sources. So whatever was true with the voltage and current sources that we've seen before, it's still true now. Linearity. All of that is still true. Thevenin and Norton equivalence. All of those concepts still hold. They are still true. The difference here is we're going to have VThev, we're going to have I short circuit, and we're going to have ZThev, but the relationship is still ZThev is equal to VThev over, I wrote VThev. It's interesting, I kind of took VThev, I'll write over I Norton. Remember, VThev is the open circuit. I short circuit is I Norton. Those two are the same. They're one and the same, one and the same. So all of those things still hold true. Now here's something else that still holds true, but there's a variation. So there are two variations, even though the concepts are the same. And those variations are, number one, superposition. And I told you a long time ago, it seems like a long time ago, we did superposition. That superposition, I told you, was stupid position because there was no need to break it up into smaller circuits. Superposition is a must in phasor circuits when you have inputs that have different radian frequencies. I want you to think about this right now. Why do you think this is true? You would have to use superposition when you have sources that have different radian frequencies. What happens when you have sources with different radian frequencies? What's going to happen in a circuit? Hint, think about impedances. If omega is equal to 1, what's Z sub L equal to? I have a 2 Henry inductor. I have a 2 Henry inductor. Omega is equal to 1. I'm going to convert that to its impedance. What is its impedance?
Is it 2?
Almost. What comes before the 2 or after it?
J.
Good. J2, J omega L. What is it when omega is equal to 2?
J4.
So the problem is this, when we have different frequencies, the impedance is changing. So what we have to do is we have to take all sources of one frequency, do the analysis of the circuit with that, and then if we have sources of different frequencies, we have to use superposition for the different frequencies and find out what the output is. So that's that variation. The other variation is the following. It's maximum power transfer. So remember, in maximum power transfer, we were saying the following. If I have a circuit that looks like this, R, and I want to know, how do I choose this resistor to maximize the amount of power dissipated in this resistor? And we know the answer is choose R sub L to be equal to R. But the difference is we have this circuit now. We have two possible circuits. We have one that looks like this. Over here, C sub L. So that's one choice, and here's another choice. And we're going to save this till we get to the power part. I just want it to be a resistor, or I let it be a completely complex impedance. How do we select either of those to dissipate the maximum amount of power in here or in here? Don't answer the question. We'll figure that out later. So there is a variation to that. Otherwise, the concepts are all the same. These concepts are the same. So let's apply the concepts to circuit analysis. So here's what I'm going to tell you. This is the basic process that we're going to use when we do circuit analysis. So let's recall what's going on. So, one, we are given a circuit in the time domain. Your author of your book gives you a lot of them in the frequency domain, but we know in the real world, we get them in the time domain. So you're given a circuit in the time domain, and the circuit has sinusoidal inputs. So that's the case. Two, we want to solve for only a forced response. Or what's called the sinusoidal steady state response. So it's important, we only want that, because if we want the transient response, the homogeneous response, the natural response, the transient response, a lot of people call it the transient response. If we want the transient response, this doesn't work. We've got to go to the differential equations method. Or wait a chapter or two until we talk about another concept that we can use called Laplace transforms. So we want to solve for only the forced response. Okay, so what do we do? Convert the circuit to the frequency domain. Okay, I'm going to tell you exactly what that means. One, all voltages they become phasor voltages. Example, V1 becomes V1 phasor. All currents. So if there are any currents and voltages labeled, you change them over to phasor currents in phasor voltages. So we convert that. Inductors. Capacitors. So when we convert the circuit to the frequency domain, we're changing currents and voltages, and then we're changing our capacitors and our inductors. Obviously, resistors are staying the same. So we're converting our circuit. Now, once we've converted the circuit, use your preferred circuit analysis technique to solve for the desired result. I don't know what the result is, but let's assume that it's either a current, this is either a current or a voltage. Okay, so assume it's either a current or a voltage. If it is, convert if necessary. The current or voltage to polar form. So if it's in rectangular form is no good for us. You got to make sure you put it in polar form. Obviously, when I say put it in polar form, you can put it in exponential form because exponential and polar really are the same thing. So we do that. We put it in polar form. Now, why? Because we need it in polar form if we're going to convert it back to the time domain. And obviously, we want to solve the problem in the time domain. So we're going to convert the desired phasor to the time domain. And then solve the problem. I don't know what the problem is, but solve the problem. Usually 5 solves the problem. So here's what goes on. Squeeze this down a bit. So we start and we figure out, hey, I have a sinusoidal circuit, sinusoidal inputs only, so I can use this phasor method because they only want the forced response. So I convert the circuit. Here, I'm going from time domain to frequency domain. I do all my work in the frequency domain. Work in the frequency domain. Why? Because it's easier. Then here, convert back to the time domain. And that's where we want the answer. The answer is in the time domain. So we've got to convert back to the time domain. And then we solve our problem. Great. Let's see that in action. So here's our first circuits problem. Ten cosine of 2t. So I have this beautiful series RLC circuit. Circuit that your authors have focused on at length in this chapter. I'm not going to focus on, actually not so much on this in this chapter, in the previous chapter. Okay, here are the values. 3, 1/4, and 3. In here, I want to find the voltage across the inductor. So let's call that V. find the steady state voltage V. Find the steady state voltage. Okay, so we don't care about the transient response. We just want the forced response. And that's always the case in these phasor circuits. It's rare that we want the transient response. So step one, and you should be thinking of doing this in different colors or redrawing the circuit. But I would recommend that you don't redraw the circuit. So draw the circuit large enough so that there's enough space to put the following on. So 10 is going to be 10 at an angle of 0. That's the phasor domain. I'm going to circle or box everything that's in the frequency domain. That's wicked easy. Scratch pad over here. I have minus J over omega C. That's my formula. Minus J. What's omega equal to? Value of omega?
Is it omega?
Nope.
2.
Correct. Right there. You get to, we've used omega so much, now we get to use it. We look at the source and we figure it out. So omega is 2, so that's 2 times C, which is 1/4. So this is minus J over 1/2, which is minus J2. For the inductor, we have J omega L. Omega is still 2, and L is 3. So over here, I'm going to put in J6. And this, I'm going to change to V phasor. Okay, now we've got a pretty simple circuit. What do you want to do? Mesh analysis, nodal analysis, voltage divider, current divider, superposition, linearity. What do you think? We're solving for V. Think of every element in this circuit like they're all resistors. They're all impedances. Think of them like they're all resistors. How would you solve this problem? I'll tell you how I would solve it. I would use a voltage divider. So I want the voltage across this impedance here. So it's the impedance of where I'm looking for the voltage. So V phasor equals J6 divided by the sum of all of the series impedances, 3 minus J2 plus J6, all times the voltage across the entire impedance. From there to there, the voltage across the entire impedance, times 10 at an angle of 0, which is nothing more than 10. So this equals J6 divided by 3 plus J4 times 10. I can take that 10 and throw it in the denominator, but I'm just going to hold it off. And this is what I'm going to do. I'm going to clean this up by multiplying by 3 minus J4, 3 minus J4. So when I do that, I get the following. In the numerator, I get this J6 times minus J4. The J's with the negative sign become positive, and that's going to give me a positive 24. So it's going to be a 24. Then the J part is going to be J6 times 3, J18. So there's all of that. There's my 10 that I still have in the numerator. And we know in the denominator what we're going to get. We're going to get 3 squared plus 4 squared. All right. Let's see what we can do. So I can factor a 6 out. So that's going to give me 60 times 4 plus J3, all divided by 25. 60 divided by 25. Well, certainly 5 goes into 60. Goes into 60 12 times. 12 fifths. 4 plus J3. Great, we've done all of it, our dirty work. But we're after little v. This is cap V. So notice what we want to do in step 5. Or actually, step 4. Step 4. Convert, if necessary, the current voltage to polar form. So right now, we're not in polar form. So let's continue this. This is equal to 12/5 times the square root of 4 squared plus 3 squared at an angle tan inverse of the imaginary over the real, 3/4. Fortunately, this is a pretty nice number to work with. Square root of 25 is 5 at an angle of tan inverse of 3/4. And so those 5's cancel. And this is equal to 12 angle tan inverse 3/4. Beautiful. Now all we're left with doing is converting this back into the time domain. Therefore, not equals, therefore, V equals 12. Now here's the part I didn't carry around. I'm just going to put it back in. Ready? Cosine of 2t. All of that we took out at the beginning. Let me get rid of this. We took all of that out at the beginning. We just put it back at the end. Plus tan inverse 3/4. Units are volts. You decide whether you want to go through the differential equation to solve that problem. And if you like the differential equation to solve this problem, God bless you, go ahead and do it. So process, not too bad. I like it. Let's do another one. Okay, given the circuit, find the force response for V1. So I have 10 cosine of 3t, 10. Capacitor value is 1/30. And over here, I have a current source. This current source is sine of 3t. Make sure that looks like a 10 right there. And here's what we want to find. We want to find this voltage right here, V1. Clearly, if I find that voltage, I can find the power delivered by that source. It'll be a time varying power, but that's okay. We're not bothered by that at all. Okay, so we're going to convert this. Well, to convert this, I need to do something in the time domain first before I convert this to the frequency domain. What do I need to do in the time domain? So look, critically important. Same frequency. They must be the same frequency. So they are. Same frequency. But the problem is, one is a cosine, one is a sine. What reference do you want to use? Sine reference or cosine reference?
Cosine.
Cosine is what's typically used. If there was only one source, and that source was a sine, I would use a sine reference. All that means is the following. You do all of your dirty work, then when you go backwards to here, you put in a sine rather than a cosine. That's all that means. Well, so we're going to choose a cosine reference. That means I need to choose this in a way that it looks like a cosine. I need to convert it. So let's convert it. See if you agree with this. Sine of 3t is the cosine of 3t minus 90 degrees. All right, now we have our circuit in a form that we're ready to convert it. So here goes. This is 10 at an angle of 0, which is just 10. Anytime you have a pure cosine like that with no phase shift, it's just a pure number. This 10 here is just 10. Now I have 1/30th. So just a reminder, J omega L is for inductors and minus J over omega C is for capacitors. So that's what we have here. We have a capacitor. This is minus J over omega. Omega is 3 times C, 1/30th. We don't have an inductor here. We have a capacitor. So this is going to be equal to, oh, beautiful, minus J10. For this, converting this is going to be, notice out front there's a 1 at an angle of minus 90 degrees. A 1 at an angle of minus 90 is a real nice number. That number is minus J. All right, so we've got that. Now we need to convert this. I'll put it on the inside. Is my V1. Okay, question is, how do we want to solve this circuit? Mesh or nodal analysis? Well, we're after V, so I think nodal analysis, there's one node, there's one mesh. If I call this my reference down at the bottom, do you agree that this node up here is V1 phasor? Everybody agree with that? Okay. So now what? Now we just use the nodal analysis method. So here we go. This node right there has a node voltage of 10. It's 0 here. So 0 and I rise 10 is my 10 that I rise, all in the frequency domain. So that voltage is 10. So I have at V1, we have the following. We have V1 minus 10 divided by the impedance, 10. Plus, down the middle, V1 over minus J10. Thank God for nice numbers. Minus, because the current's coming in, minus a minus J equals 0. Minus a minus J. All right? So what do? Clean denominators. How do I clean the denominator? If I multiply by minus J10, actually, let me show you something that a lot of people do. I like doing this. So right here, that negative J, right now I'm going to move it to the denominator. I can do that because it's a multiplier down there. So 1 over minus J is a positive J. So there it is. It's a positive J, and now it's not a negative J in the denominator. Now all I have to do is multiply by 10. So when I do that, I get V1 minus 10 plus JV1. And if I bring this to the other side, which I will do right now, it's plus J. Over the other side, it's equals minus J. So I have what? For V1, if I add those together, I get 1 plus J V1 equals, going to bring the 10 over to the other side, 10 minus J.
Isn't it minus J10? When you multiply the whole thing by 10?
This one here, correct?
Yes.
Thank you. You're awesome. Again, that is minus J10. You're so good. I so appreciate you. Yes, it is. Okay. So I just divide. V1 equals 10 minus J10, which I know you know I can factor some beautiful stuff out of there, divided by 1 plus J. So equals 10 times 1 minus J divided by 1 plus J. Always do that if you can, unless you see a good reason to leave it in there. Because if you can minimize the sizes of your complex numbers, when you're doing your complex number arithmetic, it'll be a lot easier. So I'm going to stop right here, and I want you to tell me what I should do next. What should I do next in this mathematics? Multiply by what?
One minus J over 1 minus J.
Thank you, Connor. Indeed, indeed. So that'll clean up the denominator nicely for us. That's going to give us 2 in the denominator. 1 squared plus 1 squared. In the numerator, I still have this 10. Now I have the following terms. Ready? 1 times 1, that's 1. Minus J times minus J is minus 1. So that's 0. And then the J term. This J times that, minus J. This times that, minus 2J. So all of this equals 10 times minus 2J divided by 2. Let's cancel that 2 with that 2. That's equal to minus 10J. Is that the form we wanted in? We've done all of our nodal work. We found our desired variable. What form do we want this in?
Polar form?
Good. So tell me what is polar form. Marcel, I think that was you. Tell me what's polar form for minus 10J. Anybody?
Would it be 10 to the angle of 0?
No, not 0. Close.
Is it 3?
No, for the angle,
Negative 90.
negative 90 degrees. Imaginary axis, real axis. 0 on the real part, minus 10 on the imaginary part. We're right down there. Negative 90 degrees. Good job, Connor. So, therefore, V1 equals 10 cosine of 3t minus 90 degrees. You could leave it like that if you want to. I'm recognizing, son of a gun, cosine of 3t minus 90 degrees. Well, that's the cosine shifted quarter of a cycle to the right. That's a sine. This part that I just did here, you're not responsible for that. If you know it, do it. It's awesome. Put in my volts. Here's my answer. I challenge you to get that answer using differential equations. It's not overly hard. I just challenge you to do it. It's just more work. It's just more work. Okay, let's try another equation, another circuit. You can never do enough of these. I'm not sure if we'll finish this one, but I think we will. On the state voltage. And we'll make this one V. All right, larger circuit. That means mathematics gets uglier and uglier, typically. Okay, so I'm going to have a circuit that looks like the following. I want to put a capacitor here. And down here, I want to put an inductor. And then over here, I'm going to put an inductor. And I'll put a capacitor. And then across the middle, I'm going to put a resistor. This capacitor value is 1/4. This inductor value is 1/4. This inductor over here is 1/4. This capacitor is 1/4. And the resistor in the middle is 1. So some nice, easy numbers to work with. And this is 2 cosine of 8t. And the voltage that we want is this one right here. I want to find that voltage. So let's go ahead and get that circuit down. We've got 10 minutes to see if we can solve this circuit. I want you to observe immediately that this circuit has 4 storage elements. This would lead to a 4th order differential equation. A 4th order differential equation. You don't want to have to find that 4th order differential equation. It would be nearly impossible for you to find it. That's why this phasor method is so important. Okay, here go my conversions. So pretty easy that all of these are the same. So just as a reminder, sometimes it's important to write this. Sometimes I find it that students find it valuable if I do this. For this circuit, omega is equal to 8. So every time we're using omega, omega is 8. So minus J over omega C for those 2 capacitors is minus J over 8 times 1/4. And so that's equal to minus J 1/2. So this capacitor minus J 1/2. This capacitor minus J 1/2. Let's do the inductors. Minus J omega L is equal to minus J times 8/4. And both of those are going to be not minus. I don't know where the minus came from. Until these 2-hour lectures are getting long. Just J omega L. And so that's going to be J2. So this over here is a J2. And this one over here is a J2. And the only thing left in the circuit elements is the source. This source is 2 at an angle of 0, which is 2. This voltage V here is V, and this 1 ohm resistor is the same in the frequency domain, no change. Okay. Mesh analysis or nodal analysis. So how many mesh equations would there be? Number of mesh equations?
3.
3, that's correct. 3 loops, no current sources. How many nodal equations? Well, let's see. Let's find the nodes. There's 1. There's 2. There's 3. There's 4. Minus 1 for reference, that takes us down to 3. Minus 1 for a supernode, correct? So here's a supernode from here down to there. That's a supernode. So there are 2 nodal equations. 2 nodal equations, 3 mesh equations. I'm doing nodes. Now the question is where we choose the reference. And everybody might have their own choice about where to choose the reference. There are 2 good choices. The one on the bottom, that's your standard. That's a good choice. That works. That's what most of you like. You like that one there. The other good choice would be this one right here. Okay? And the reason that would be a good choice is because then this node voltage right here that I'm coloring in real dark would be V. That would be the node voltage. So you could do that. I'm not going to do that. It's going to save us a whole heck of a lot of time. So I'm not too worried about that. So let's get rid of that and let's not do that. And let's choose our reference down the bottom. So if I do that, I'm going to call this V1. I'm going to call this V2. And I'm going to call this up top. Obviously, it is 2. Everybody see that? It's 2. Ground at the bottom, 2 at the top. at V1. So I have V1 minus 2 divided by minus J 1/2. I'm going to tell you what's really cool about that in a moment. Plus V1 minus V2 divided by 1. That's awesome. Thank you for the nice numbers. Plus V1 over J2 is equal to 0. Let's clean that up. Look at this right here. This is the same as the following. I'll rewrite this equation. It's the same as J2 times V1 minus 2. Because the 1/2 flips, gives me a 2 in the numerator. 1 over minus J is positive J. Plus V1 minus V2. And then here I'm left with plus V1 over J2. But I can take that J and I can put it as a minus J in the numerator. So let's do that by just making this minus J. And now there's a 2 equals 0. Just take this equation, multiply by 2. So they're not all that easy. They don't all work out to be really smooth. But this one works out pretty good for us. And so I'm going to do it like that. So what I'm going to do now is I'm just going to multiply through by 2 to get rid of that 2 that we have in the denominator. So when I do that, I get the following. This is J4 times V1 minus 2 plus 2V1 minus 2V2 minus J V1 equals 0. Group all my terms. So my V1 terms, let's see what I have in my V1 terms. So V1, I have a J4, I have a 2 plus J4, and then I have a minus J. So that's going to be 2 plus J3. 2 plus J3 V1. Now for my V2 term, I just have a minus 2 V2. And let's bring all the constant terms over. And so my constant term is this with that. It's minus J8 on this side, positive J8 on the other side. I think I got all my terms. So that's one equation right there. Box that. That's one equation. Hang on to that. Let's go back upward and let's get the second equation at V2. So at V2, let's see what I have. I have V2 divided by minus J 1/2. That's the current going down. Plus V2 minus V1 over 1. That's the current going across, and then the current going up. Plus V2 minus 2 over J2. Very similar equation, equals 0. Again, this first term is just J times 2 V2. Just remember that. Plus V2 minus V1. And then minus J. And then V2 minus 2 over 2 equals 0. Take that one, multiply that by 2. It's going to give me J4 V2 plus 2V2 minus 2V2. Now, that 2 will cancel and I multiply by 2. So I'm going to get minus J V2 and then plus 2J equals 0. All right, that's that equation. Let's bring this down. Let's clean it up. So if we clean it up, let's get all the V2 terms. Something screwed up. This is a V1 right here, right there. V1. Okay, so my V2 terms. There's a J4 minus a J, that's J3. There's 2 plus J3. That multiplies V2. Then I have a minus 2V1, minus 2V1. And all of that equals negative 2J on the other side. Good. Now I have these two equations. Question is, what do we need to solve for? So, what do we need to solve for in that circuit? What do we need to solve for? Well, we need to solve for V. What is V equal to in terms of the circuit variables? terms of our circuit variables, what is V equal to?
V1 phasor.
I got the first part, Jordan. I think we know, maybe it's Connor.
Is it V1 phasor?
Nope, it's not V1 phasor. Look at V. Look at the plus side, look at the minus side. Connor, what do you have?
V1 phasor minus V2 phasor.
Yes, V1 phasor minus V2 phasor. So tomorrow, or which is Monday, when we're back together, we're going to solve V1 phasor minus V2 phasor. What I'm going to do right now for you is I'm going to give you some homework problems for those of you who want to work on the homework. Let me jot those down for you so you can see them on paper. So let's pull up my pad. Good. So the homework problems that you can start on in your analysis, chapter 9, page 362. They are 12A, 15, 27, 28, 31, 45, 46, 64, 68, and 70. I believe you can actually do each of these. One of these problems is a superposition problem. There are two Thevenin problems. There are just regular circuits problems. There are current dividers, voltage dividers, a variety of different things in those problems. But I believe you've got the skill set to do all of those. Okay, and we'll take a look at one or two of those problems on Monday. Terrific. Any questions before we part ways for the day? Everybody stay safe. Have an awesome, wonderful weekend. Work on a few of those problems. Get a head start on those. We will have a quiz on Monday. We will have a quiz on Monday. Anybody want to throw out a topic that you want to have a quiz on Monday? A realistic, reasonable topic? Finding the differential equation from a circuit, second order differential equation from a circuit. You think you can handle that?
Yeah.
Okay, I won't make it too hard. Let's plan on that. Get the second order differential equation from a circuit. It won't even be to solve the differential equation. I'm assuming you know how to do that. So plan on that on Monday for a quiz. Have a great weekend. Stay safe, stay away from people, and I'll see you on Monday.